Imagine the universe billions of years ago, not galaxies, not stars, not even atoms. Just a singular, infinitely dense, and incomprehensibly hot point. From this enigmatic beginning, everything we know, see, and experience has emerged. This, in essence, is what the Big Bang Theory describes, the dramatic story of the birth and evolution of the cosmos. The Big Bang Theory is not just a moment, but the most widely accepted scientific explanation for how our universe originated and has continued to change. According to this theory, about 13.8 billion years ago, the entire universe began from a state much smaller, hotter, and denser than anything we could ever imagine. A state in which the very fabric of space and time itself was compressed. In a sudden, mind-boggling expansion, this tiny seed of the universe burst forth, sending energy and matter outwards, setting into motion the continual expansion that persists to this day. It can sometimes be tempting to imagine the Big Bang as a loud explosion at a particular place in space. But in reality, it was not an explosion like a bomb going off, scattering debris into empty surroundings. There was no outside into which the universe could expand, because the outside did not exist. The Big Bang was quite literally the rapid expansion of space itself, and every point in our universe today traces its roots back to this same origin. The entire cosmos was born everywhere, all at once, from this singular event. But how do we know any of this? What evidence has convinced scientists that such a momentous event actually occurred? The answers lie in several extraordinary observations and measurements, each one a puzzle piece that helps us reconstruct the universe's earliest moments. First, let's consider the cosmic microwave background radiation, or CMB for short. In 1965, two radio astronomers, Arno Penzias and Robert Wilson, unintentionally discovered a faint, uniform glow of energy that filled the entire sky. This wasn't just random noise. It was the oldest light in the universe, a relic from the time when the cosmos was just 380,000 years old. Back then, the universe had cooled enough for atoms to form, allowing light to travel freely for the first time. This released a flash of energy, still detectable as a uniform, low-temperature glow today, like the lingering warmth from the universe's fiery childhood. The existence and characteristics of this CMB perfectly matched what the Big Bang model predicted. Second, there is the phenomenon of redshift. When we look out into the night sky, we're peering back in time because light from distant galaxies takes millions and even billions of years to reach us. Astronomers discovered that light coming from these remote galaxies appears stretched, shifted toward the red end of the spectrum. This stretching happens because space itself is expanding, carrying galaxies away from us. The farther away a galaxy is, the faster it appears to be receding. This pattern correlates beautifully with what the Big Bang Theory predicts, a universe that began small and dense and has been getting larger and more spread out over time. Third, there's the chemistry of the cosmos. In the minutes after the Big Bang, the universe was a sizzling soup of subatomic particles, protons, neutrons, electrons. As everything cooled, these particles fused to form the simplest elements, mostly hydrogen and helium, with small traces of lithium. The abundance of these light elements we see in the universe today matches, with remarkable precision, the ratios predicted by calculations based on the Big Bang Theory, a process known as Big Bang nucleosynthesis. Taken together, this trio of evidence forms a powerful, self-consistent narrative. The cosmic microwave background reveals an early, hot, uniform universe. Redshift tells us that the universe is still expanding, just as the aftermath of a bang would predict. The chemical makeup of matter matches what would be formed in such a fiery beginning. Let's pause to imagine those first colossal moments. In the first fractions of a second after the Big Bang, the universe was unimaginably hot. A dense, seething plasma in which particles collided at tremendous energies. Then as it expanded, it also cooled. Dramatic changes followed. Bursts of energy created a zoo of subatomic particles. Inflation, a brief period of exponential expansion, smoothed out the cosmos and set the initial conditions for galaxies to form. Within 3 minutes, most of the hydrogen and helium in the universe formed. A remarkable calm gradually settled over the universe as it continued to cool. Hundreds of thousands of years later, atoms finally came together, letting light travel freely for the first time. A moment forever echoed in the cosmic microwave background. But at this stage, the universe was still dark, a nearly featureless sea of gas. Only hundreds of millions of years after the Big Bang did gravity begin pulling together clumps of matter, lighting the first stars and galaxies. These first stars illuminated the cosmos, forged heavier elements in their fiery cores, and upon dying, they scattered their enriched ashes, seeding future generations of stars and planets. Over billions of years, these building blocks formed greater and more intricate structures. Galaxies spinning with billions of stars, solar systems, planets, and eventually, somewhere on a small rocky planet circling an ordinary star, life itself. Despite its elegance and explanatory power, the Big Bang theory is sometimes misunderstood, leading to common misconceptions. For example, many people picture the Big Bang as an explosion that happened at a particular spot in the universe. In truth, it happened everywhere because it was the expansion of space itself. No matter where you are in the universe, you see the galaxies around you receding. The expansion looks the same everywhere. Another misconception arises from the question, what happened before the Big Bang? This is a tricky one, because according to our best understanding, time itself began with the Big Bang. Asking what came before may not even make sense, since there was no before in the absence of time as we know it. Our conventional picture of cause and effect breaks down when discussing these earliest moments, challenging even the most creative scientific minds. It's also important to realize that while the Big Bang theory explains how the universe expanded from an early, hot, dense state, it does not necessarily tell us what caused the origin of that state itself, nor what, if anything, initiated the process. These deep questions remain the subject of ongoing research and intense debate. Scientific theories are always improving as we develop better observations and deeper understandings. Over the past century, discoveries in astronomy, physics, and mathematics have all contributed to our evolving model of the universe's origins. Tools such as powerful telescopes, sensitive detectors, and advanced simulations have allowed us to peer ever further back in time. Observations of galaxy formation, measurements of the cosmic microwave background, and studies of how structures evolve on cosmic scales all reinforce the Big Bang theory's predictions. There continue to be mysteries. For example, as astronomers looked more closely at how galaxies rotate and move, they realized visible matter wasn't enough to account for their behavior. A clue to the existence of dark matter, an invisible substance that exerts gravity across the cosmos. Likewise, the mysterious dark energy is causing the expansion of the universe to speed up, not slow down as once thought. These discoveries, while not contradictory to the Big Bang theory, add layers of complexity and point to tantalizing gaps in our understanding. The Big Bang theory is striking not only for its scientific accuracy, but also for its philosophical implications. It tells us that everything, every star, every tree, every atom, originated in a single shared moment. The carbon in your body, the oxygen you breathe, the iron in your blood, all trace their origins to the hearts of ancient stars that lived and died billions of years ago. We are, quite literally, children of the stars, connected by a grand narrative that stretches back almost 14 billion years. So when you look up at the night sky or gaze at the Milky Way arcing overhead, remember, you're not just looking at distant lights across space. You're peering back in time, witnessing the universe's ongoing story, a tale that began with the Big Bang and continues, not just to unfold in the farthest galaxies, but in every atom, in every living thing, and in every moment of wonder. In summary, the Big Bang theory is our most compelling and broadly supported scientific model for the birth and growth of the universe. It draws together evidence from the faint afterglow of the cosmic microwave background, the relentless expansion seen in redshift, and the elemental makeup forged in the universe's earliest minutes. It challenges us to reconsider our notions of time, space, and existence itself. And it continues to evolve, inspiring new generations of thinkers to push the boundaries of what we can know about the cosmos and our place within it. As our instruments and theories become ever more sophisticated, we will no doubt refine and perhaps radically reshape our understanding of the universe's beginnings. But for now, the Big Bang Theory stands as a testament to humanity's ability to observe, reason, and imagine, all in pursuit of the ultimate questions. Where did everything come from? And how did we get here? In every answer we find, the story of the universe becomes richer, and our sense of connection to the cosmos, stretching from the instant of the Big Bang to the present day, becomes ever more profound.